Thank you very much for the introduction. Hopefully you can all hear me. That seems pretty good. That's excellent. Yeah, it's an absolute pleasure to be here today to deliver this talk. I come to Cambridge quite a bit. My uncle just sat in the crowd who was a Clare College alumni, did his undergraduate here many years ago. So I often make the trip, but not always to the university. And yes, as alluded to, it's going to be a very, very varied talk today. So we're going to go a little bit through sort of my passion for chemistry and the baking. It'll be remiss of me not to mention the bake-off, so be prepared. There's going to be quite a lot of cake I'm going to show you. We're going to go through my actual research, because often people, when they see me having come off a television program like the bake-off, they think I just make cakes all day. Well, I do actually do research as well, so I'm going to talk about the research and then a little bit about the science communication that I've been able to do really in the last 18 months on the back of the platform that Bake Off's given me. So, without further ado, first slide really helps sort of like tell the title of the talk, Out of the Lab and Into the Tent. So, yes, in 2023, I went out of the chemical biology lab into the famous white tent of the Great British Bake Off. So, this is me only a couple of years ago in the chemical biology lab, top floor of the School of Chemistry, University of Leicester. And then this obviously is when I got all the way through to the final of the Bake Off in 2023, alongside my fellow finalists, Matty and Dan. We've got Paul Hollywood, we've got Dame Prue Leith, and then the presenters, Alison Hammond and Noel Fielding. The most amazing experience ever. And yeah, I still can't believe now, having been such an avid watcher of the show for many, many years, to then actually now done it and gone all the way through. Yeah, it's still quite surreal. I can't believe it's happened. So, yes, but I think all the way through, and anybody that did watch on the show, I think that my science came through very strongly on how I sort of prepared the bakes, how I sort of approached putting them together. I mentioned them quite a lot as well. And so I thought where I'd start is I'd go right back to sort of where did my passion or love for both the baking and the chemistry come about, but in particular the love of chemistry. So what I've got here is I just put a slide. I was thinking back to where was one of those first sort of reactions that I'd done, practical reactions in chemistry I think it would have been probably GCSE on the GCSE A level with my chemistry teacher, Mr. Reed. And I thought back to, this is the one that I always remember in the back of my head, making aspirins, one of the classic ones they always do. Salicylic acid, we've got our acetic anhydride, bit of acid catalyst, we warm it up, usually might have been over like a Bunsen burner flame or in a water bath, and then we make our aspirin. But before that, I've always had a big love for the baking and mixing ingredients together and getting a product at the end. And I think this is the sort of time when I really realised quite how much chemistry is baking. They're very much more on the same, and I had such a drive to want to be able to do more of that and make molecules and be able to follow that process. So that's making aspirin, but how my head works, I see it in exactly the same way as when we're just making things in the kitchen as well. So it's all the same. We're mixing ingredients together or reagents together in a pot. We're weighing them out accurately. We're following a method, and we get a product at the end. So there's so many overlaps all the way through. So I just listed a few down the side there, and I've always thought that there has been so many overlaps, but Bake Off really drove home to me quite how many overlaps there is. So like I said, we're following a procedure, we're weighing things out accurately, we've got this stepwise addition, we must do things in a very particular order. You know, if we didn't pre-cool down our flask before adding a reagent in the chemistry lab, it's going to affect the reaction, especially if you're trying to get a stereo-controlled reaction. Same as when we're doing our baking, there's certain bakes, you have to do things in a certain order. You can't follow the recipe and do steps 1, 2, then go to 5 and come back to 3, because you're going to mess up the bake. So it is very much the same. We use catalysts in our chemistry. So again, we use an acid catalyst there, but we use catalysts in our baking as well. So we've got biological catalysts. We've got our yeast that's helping to make our bread to rise. There's so many enzymes that are going on in our mixing bowl when we're making some bread. Then we've even got things like baking powder for our cake. Again, a substoichiometric, a tiny amount of baking powder that we're going to mix into our cake batter, and we know it helps give us a lovely light sponge. So there's so many overlaps between the two. We get a lovely product at the end. Obviously, the product in the chemistry lab we can't eat, whereas the one at home we can. And then the thing that really drove home to me from the bake-off was scale up. So having to do those bakes on such big scale, that's where I really realised that my grounding and experience as a chemist really, really helped, because it's only then when you realise it's such hard work. So baking on big scale for the bake-off, everything takes longer to weigh out. You know, one of the bakes I would remember zesting at 12 lemons for a bake. I mean, when would you normally zest 12 lemons at once at home? And then but things take longer to bake, longer to put together, longer to cool. You might have to do 2 goes in the oven, longer to decorate. Everything takes longer, but it's exactly the same when it's in the chemistry lab. Your reactions, again, things take longer to weigh out. They take longer to happen. The purification takes so much longer as well. But the biggest thing is the washing up, I would say. The washing up on the bake-off, well, I didn't actually have to do it on the bake-off. Somebody comes and does it for me. But definitely something that I can relate to as a chemist in the lab would be, again, once you scale up a reaction, everything, there's just so much glassware you've got to wash up afterwards, and it's such hard work. But again, I've got the skills from both. And then the other thing is not always a success. So sometimes chemistry doesn't work, or most of the time science doesn't work. I think anybody that's involved in science would attest to that. But it's the same in the kitchen as well. Sometimes it doesn't always work, but you can learn from it. You can go back to the drawing board and you can tweak around with things and you can try and get it better next time. But at least when it goes wrong, when you're baking something, you usually can still eat it. Whereas when we do it in the lab, we've got to start again and wash it all up. So that's really the sort of how my mind works, the overlaps that I see between baking and chemistry. So now I'm going to go back and talk a little bit about my chemistry at Leicester, and then we'll have a few little links into baking along the way. So I've been at Leicester now for 11 years. I did my undergraduate in pharmaceutical chemistry, PhD, and then postdoc research started in 2022, and then bake-off started right at the start of 2023. So first year of postdoc was a busy year, very, very busy indeed. But it's been really great to be, to be the student, then be the PhD researcher, doing your own research, but then being able to give back and actually demonstrate for a lot of the undergraduates in the teaching labs. I've always been involved in the science communication at Leicester, so this is making our liquid nitrogen ice cream that we always do when it's ever an open day or anything like that. So I've loved to be a part of that all the way through. But I thought what I'd do, I'm going to touch upon some of my research, just so, like I said, just so I can prove to you that I am actually a researcher, as I don't just make cakes all day. So my research at Leicester, the proteins that we was in the field of targeted protein degradation. So the class of enzymes or proteins that we were targeting are histone deacetylase enzymes. We've got some real world leaders in these particular enzymes, HDACs, at the University of Leicester, on both the sort of the structural elucidation and the cellular biology behind it as well. And these are these epigenetic regulators. They catalyze the hydrolysis acetyl groups, are mainly on histones. And the histones, they exist as an octamer. They are they're what make up our chromatin fiber in our chromosomes. There's an octamer, they've got the DNA wrapped around them, and they can be subject to a variety of different post-translational modifications. So we can have methylation, demethylation, phosphorylation, acetylation, ubiquitination, all different ones. These sort of different modifications, these act as these like molecular switches, and they can sort of like help sort of like, they alter the sort of compaction of our chromatin, and they can signal for whether we've got gene activation, gene repression. In the case of our HDACs, they are serving to deacetylate, so we're taking off the acetyl groups of our lysines. We're freeing those up now, so they're now charged. They can now interact with, bind to our sugar phosphate backbone, get interaction. We get this compacted chromatin now, and that can signal for gene repression. HDACs are overexpressed or dysregulated in many different disease types, including cancers, and therefore they're a really important target for us. In particular, though, because these HDACs, there's many of them. So they exist as 18 different ones in the human genome. They're split into 2 different types. We have zinc-dependent, we've got NAD+ dependent. We're particularly focused on the zinc-dependent ones. They're the ones that are primarily involved in the histone deacetylation. In particular, class 1 HDAC. This is 1 to 3, and there's 8 as well. But 1 to 3 are the ones we're particularly focused on, because these HDACs, they exist in cells in the nucleus as part of these multi-protein co-repressor complexes. And there's lots of examples of HDAC targeting as inhibitors, and we can target class selectively, so we can target like class 1 HDACs, but it's been really hard to be able to get subclass selectivity and target individual HDACs, particularly these ones that exist as part of these multi-protein co-repressor complexes. So we have examples where we've got the same HDAC, but they're present in different complexes. So we wanted to try and find ways of probing those selectively and see if we could work out more about their function, but also be able to target them and degrade them selectively as well. So that's the HDACs. The methodology that we wanted to target them with was targeted protein degradation using the class of molecules methodology called PROTACs. And these are proteolysis targeting chimeras, and these are these bifunctional molecules. They've got an inhibitor at one end, so we've got a HDAC inhibitor that's joined together via a linker to an E3 ligase ligand, And I've just got a little scheme here to show you the process by which this sort of methodology works. So what happens is the inhibitor end recruits our HDAC. Then the other end now is serving to recruit this E3 ligase ligand. It's got a conjugated E2 ligase and this ubiquitin protein. And what we've done is the PROTAC has served to bring these two protein entities together. By bringing them close together, it's now spatially favorable to be able to induce this transfer, this ubiquitin protein, over onto our protein of interest, our HDACs. This can then happen multiple times. We can end up with this polyubiquitin chain. This polyubiquitin chain now almost acts as a stamp, as a marker now. So when it is seen by the proteasome, it can then be selectively targeted for degradation. So it is degraded. So in comparison to your classical sort of inhibitor approach, you've got that lock and key model where you're binding to your protein. It's still there, but you just blocked its activity. This methodology is looking to you're binding to it, but then you're actually degrading, removing the protein completely. And this can happen catalytically, so the protein can do multiple rounds of degradation. So therefore, you can have hopefully low levels of the PROTAC, but it can keep going around. It keeps the levels of the protein low, and therefore it's a really great methodology to look to target them. And there's many PROTACs that have gone into later stages of clinical trials. But this was the first example of PROTACs to target these class 1 HDACs, which is what I did as part of my PhD. And so, oh yes, we've got cake. So, always wanted to bring my baking into my research. So this is something that I did. I think this might have been during COVID, I think. There was a bake my research trend going around. So I made my research in cake form. It all got shared up in the department. And I remember that almost like the godfather of sort of like the PROTAC technology, which is Craig Crews. I remember when I posted this on Twitter, and I remember him interacting to it and saying it was as good as ones that he's seen in manuscript. So that was a very nice praise to receive. So that's that. And then I'm going to show you the structure of the molecules. So what I used was this inhibitor here, CI994. This is it bound into the active site. You can see that we've got this acetyl group is surface exposed. It's available. We served to wanting to build off of that site, so we could build out of the active site and make it into this PROTAC. So we built off of that chain, and we had it conjugated a linker, E3 ligase ligand, and then I've skipped about 2 years here, but this is an example of a molecule that did work, JPS016, and I've got a Western blot here to show you as it works. So this is now Western blot giving you the levels of the different proteins following treatment. So I cultured HGT116 colon cancer cells, and I would drug those with my PROTAC that I got to make myself. It's amazing to be a part of the whole process, to be able to design, synthesize, purify your compounds, take them over, do all the cell culture, and then be able to actually drug those and get all the results back, do all of the Western blotting, and see it basically from conception through to end result. And you can see here, HDAC1, we can see the degradation as we get increasing concentration goes down. There's a interesting point here. You'll see with HDAC3, it goes down then up, like this. This is what's called a hook effect, which is very common in the PROTAC technology, which is whereby I showed you that we had that ternary complex being formed. What can sometimes happen is at high concentrations, you can get high concentrations of the two binary complexes, so it could be PROTAC and one of them, or PROTAC and the other one, and then therefore it can't facilitate being able to come together, so actually you can end up losing efficacy and it goes up a little bit. But the reason why I wanted to show that is because I'm now going to show the molecules. Don't worry, there's a lot on there. It's almost slightly to show off, but also just to show to usually to a very broad audience, just so you can see quite how much work goes into making an end product. There's a lot of work that goes on behind the scenes. And this is just a snapshot of some of the library that I made along the way, and also just showcasing how we went about getting to there. So it's all about this structure-activity relationship, this optimization to make the molecules better along the way. And to do that, we only change one variable on certain bits. So we were looking at, first of all, changing the linker here. So we've got different examples of linkers. We've got alkyl linkers, polyethylene glycol linkers, and other ones with pyrazine units in. We've then got our ones where we've done substitutions onto the benzamide, which is this HDAC inhibitor here. So with different ones, these different units can help to increase selectivity to particular HDACs. And then also we've changed the E3 ligase ligand as well. So different types of E3 ligases ligands to recruit different E3 ligases. And that was all the way through. And the reason I wanted to show that is the last slide here, because the reason why I really wanted to get into that field, and I've always had a big sort of love for sort of drug discovery and being able to, and wanted to be a part of this sort of process of being able to, I've got an end goal that I want to get to, and doing all that sort of tweaking along the way and optimizing a compound. But it relates back to, bring it all the way back to in the kitchen at home. It's like when you are baking a cake or doing something, and it's the ones where you're making a particular type of a bake, but you do it so many different ways, and every time you want to slightly better it or just change the decoration or just change one ingredient, and I can relate to it very much. So this is the ProTac library, but this is the cake library. And again, I like to show it because again, it's following the same sort of process whereby a lot of the things are the same. So there's similar sorts of techniques whereby they're all fondant-based ones. Some of these have got the same sponge on the middle in the inside, but it is very much like just being able to. I've always got that urge to want to sort of better and get better each time around, and just try and tweak things and just change things around. So that's really where they all relate. You'll see, notice there that we've got the Clare College crest for this cake. This is one I did for my uncle's 70th early this year. He's in the crowd. We've got a lot of Christmassy ones in there as well. But that's our cake library. I've got a macaron library here as well. But again, it's the same technique. So they're all a macaron. It's all the same process, putting them all together. But it is just every single time it's slightly changing the filling, changing the decoration. But it does go back to that same sort of process of going back to the drawing, not back to the drawing board, but just trying to get better each time and just tweak things around. So I can relate it, both the baking to the research. And then finally, we've got the pastry library as well. These are all ones from the last year. But again, it's very similar techniques. These have all been done in the same sort of like perforated rings. You can see that. So it's all the same sort of type of pastry, but just different fillings, different decoration, always wanting to play around, always wanting to get better, always wanting to try new things. And I think that's where the love for both of those come in. So I think now I've shown a few baking slides now, so this is a nice time to transition into the bake-off. It'd be remiss of me not to mention the bake-off. So I've got a slide here that's got a few of the highlights from the show. I'm not sure how many of you watched it, but I'll go through it anyway. So which one came first? That was the one I did on the biscuit week, which was on week 2. They got the famous Hollywood handshake for that one. So that was making a biscuit. You had to recreate your favourite meal, but in biscuit form. So that one there was done as a biscuit burger. This was some decorative pies we had to do, which are done as sunflower ones, and had fillings of, there's a pineapple and apricot, I think, in the filling there, and that was like a coconut, blackberry and apple. And this is my semi-final one, which is, I'm going to get it wrong, it's an Italian puff pastry dessert. It's like a mille fogli. It's basically the Italian version of the French millefeuille. And but it's just done as these big sheets. They're often done actually for Italian weddings. I'll do them as humongous spreads. So there'll be lots of individual sheets all put together, but they'll be about that sort of height, but they cover an entire table and you just cut a segment out, which I've seen them and they look amazing. That'd be such a great thing to have and see more of. And so there's a few of the highlights, but I thought what I've just put up, I'm just going to put up, I've already alluded to it slightly at the start, but just some of those transferable skills that I've taken as a chemist from undergraduate, PhD, postdoc research that I can that really did help me when I was on the show. And I think it's that matter of the organisation first and foremost. I think that's why there's been a lot of scientists that have fared very, very well on the bake-off, because I think there is that when you're going into the laboratory to go and put on a reaction, you're always organised, you know exactly what you're going to do, you know exactly what you're going to weigh out, you've prepared your cosh form, you're aware of any hazards and how to deal with those if something was to go wrong. So you've already got that mindset, and that was really, really helpful. Time management, always doing a million things in the lab, your own research, watching over the other project students you've got in the lab, answering emails, writing up manuscripts. There's loads of things to do. So being busy and being able to think on my feet, remain positive and do all of that, I think I take so much of that from the laboratory as a chemist, and that really helped me on the show. Taking on constructive criticism, that was something as well. Again, you take that on board all the time, peer reviewed any of your manuscripts that you've sent away and have come back. It's exactly the same kind of thing, so being able to deal with that and make it better next time round. Accuracy and precision weighing, all of those things I've already alluded to. So there was so many skills that I could take from chemistry, which really helped on the bake-off, but also there was the reverse as well. So bake-off has also helped me in ways I never imagined it would, like confidence in speaking, actually managing my time even better now. I can jam so much into my day, because when I was preparing for that, I used to work 8 till 6 in the lab. I'd get home, I'd then bake until 1 in the morning. I'd leave the washing up until the following morning, and then it'd be on repeat. At the weekends, we'd go and film the bake-off. I'd travel down on a Friday. We'd film Saturday, Sunday. I'd come back Monday morning. I'm in the lab again. And so it was just relentless for 10 weeks, pretty much. So, and I said to a few of you at the start, I mean, compared to writing a PhD thesis was very easy in comparison to this. This was hard work. So I'm just going to go through a couple of the weeks. I've already alluded to Biscuit Week. I like to show this one. Obviously, it got the handshake, but also I think it shows the scientific mind in action. This is it disassembled. And I think you can just see that accuracy, that precision, that attention to detail, wanting to have everything all laid out and then bring it all together at the end. I think you can see that's the chemist in action there, having it all looking perfect, all disassembled, and it all comes together. And I just love trying to recreate. I love doing these illusion style things. So you can see all the elements of the bake. Though this was all out of biscuit. So we had some orange shortbread that was rolled in a cinnamon sugar to make it look like some sweet potato fries. There's a Florentine biscuit coated in chocolate to make it look like a burger. There was a strawberry jam as a relish, ginger board as the chopping board. It was really great fun to design that and think all that up. Then we've got week 8 as well. Week 8 was party week. Anybody that knows me, I'm a very big lover of Christmas. My Christmas jumper collection is in the 60s and 70s now. It's bad, it's really bad. So when I saw Party Week, I thought if by some miracle I managed to make it to week 8, I'll do it as Christmas Party Week. It's the best kind of party for me. And so we did Christmas, but the bit I wanted to talk about actually was making the sausage rolls. I did a festive sausage roll, and I had put a cranberry sauce in it. But to make the cranberry sauce, I brought my own wine in from home. And again, it shows the process of, again, the chemistry never stops. So when the lab coat comes off at the end of the day, then get home, and then the apron goes on. But I do all the baking, but I'm still experimenting, always wanting to try new things while I'm at home as well. So I make my own wine. These are the grapes from the garden. I usually harvest them around about first week of November, crush them all up, and then follow all the process, adding in the wine yeast, adding in all the other steps along the way. In the demijohns, we get a lovely clear solution at the end after you added the finings. And again, there's so much chemistry in action. You've got all the two stages of fermentation. We add in our finings, which are acting as coagulants. They're going to bind to some of the undesirable flavor molecules, things like tannins, some of the polyphenols, some of the proteins, and then it'll just help them just to drop to the bottom. It just helps to remove that haziness, reduce the stringency. There's things like, again, the amount of sugar, and I've been doing this over many years, fine-tuning it, because the first one I made was not very good. But as I go along, you've got to sort of like play around with it, being able to add your citric acid and control the sort of acidity and the sharpness of the end result. But also it changes very much from when you add it to actually when you then drink it as well. So you've got to factor that in. And then we get to the bottling up stage. I usually bottle it up in December, hence the Christmas jumpers, siphoning it all off. And this is my dad helping me out. And then I got to bring this wine into the bake-off tent. So Dame Prue Leith has now tasted my wine. And I remember when we filmed that one, we had a little tumbler out, and I had to pour some out because she wanted to come and taste it so they could do it for camera. So she did it, she tasted it, she loved it, walked off, and then they said, I think just so we know we've got the shot right, we'll just film that again. They filmed it 4 times. So she had 4 glasses of wine. I know Prue likes her alcohol, so I think there was something in that. I don't think they really needed to repeat that again. But yes, we did. So I've had approval from a dame, so that's quite nice. And then what's on next? And then we'll go back to week 4 now. And in week 4, I've actually brought chemistry into the bake-off tent. I don't think chemistry's been brought into the tent quite like this before, so that was a real privilege to do. I was really passionate to want to bring chemistry in 1 week. I wanted to bring not only what my interest was, but I wanted to bring something like chemistry that's not very often seen on a program like that to a really, really broad audience. So it was chemistry overload. So we had chemistry shape. We had to make a tempered chocolate celebration box. I did it for the University of Leicester celebrating its centenary, the School of Chemistry is celebrating its centenary this year now, in May. So I did it in build up to that, it was a celebration for chemistry. At Leicester, so we had the chemistry cutouts, we've got some chemical structures on the top. I'll talk through those in a couple of slides' time. Used chemical elements, spelt out various words on the outside. Our glass blower that we've got in the chemistry department, she made me a glass stand to sit it on. Fortunately, between the weeks of filming, this one was the only one we had a 2-week gap. So I went to the glassblower Gail and I said, you wouldn't mind, would you be able to make me a glass stand? So she just turned that around. She made me 3 of them. She didn't need to make 3. And they're just all little conical flasks supported on a lovely sheet of glass. There was other bits of glass around the outside you can't quite see, but she made those as well. And actually the wooden panel came from the undergraduate teaching labs when they were doing a clear out. So I really was chemistry overload. So it was a really nice story to have very little of what I've just said made it onto actually the screen, but I know what I did. It was a bit of a shame actually how they edited it, because I said it all to them, but the way in which they edited it down so that actually when it was released, they cut all of that out and they just said they had a clip of Prue just saying, "Oh, Josh, you've lost me at the last roundabout," and it was really disappointing because I deliberately went on there to try to show something different on a program like that, and they've just sort of gone to the norm of just chemistry is too complicated, people can't understand it, we don't want to engage with it, and they just chucked it aside, which was a real shame because they had an opportunity, but that's by the by. So that's what we have, and I know I've been talking already for a long time, so I'm not going to go into too much detail, but obviously I had to do some chocolate truffles, so I did spelt chocolates on the top of there and using the chemical elements. Then there's some different structures that we had on the top, and I'll very quickly just go through a few of those ones because I did talk about all of this on the show. So things like butyric acid, as an acid you can tell it's going to add a sour taste. This is what's often found in American chocolate, and it's actually the reason why I don't like American chocolate very much. They often have this butyric acid, and you'll find it adds a slight dairy, almost rancid taste to it. It helps prolong shelf life, maybe it adds a slightly distinct note to it, but I'm not a huge fan. Oleic acid as a fatty acid, highly prevalent in hazelnut oil, in cocoa butter, being a unsaturated fatty acid. It's got the unsaturated bond in the middle. So in comparison to saturated fats, they're often ones that are going to be solid at room temperature. When we have unsaturated ones, we can get polyunsaturated as well. By having that kink in the chain, it means that those molecules, when they then pack together, they don't pack together quite as well. That lowers the melting point, which is why these then exist as oils at room temperature as opposed to solids, like your saturated fats would be. And that's why all of your nut oils and things, they are all oils as opposed to having like a fat that's might come from an animal fat. That's our oleic acid. We have got sodium hydrogen carbonate. Everybody, I'm sure, will know about that, or everyone's got it at home in their cupboard as their baking powder, or it's in their baking powder. You can buy it as a bicarbonate of soda. So that's what's helping to give our cakes that lovely rise. That's the active compound that we've got in our baking powder as well. Just in our baking powder, we've got the sodium hydrogen carbonate along with an acid, which is when it goes into liquid form and they come together, that's helping. That acid and base is helping to create some of the carbon dioxide bubbles to help give us the rise to our cake. So just when we have the baking powder, we've got the two together. When it's just the bicarbonate of soda on its own, often something like if we're doing biscuits or something like that, things like brown sugar have a level of acidity anyway, so you only really need bicarb in there because they're going to react. If you're doing a lemon drizzle cake, we've got loads of acid in there, so you should never need baking powder. You can just use bicarbonate of soda, absolutely fine. It's going to do the job. So and along with doing our acid and base, it's also going to just decompose in the heat of our oven, release the carbon dioxide and water vapor as well in that way to, again, give our sponge a lovely rise. We have got maltol here, which is one of the flavor compounds in making caramel, also when you roast cocoa beans as well. I think I might have a slide here actually with that process on. Often, I've not done it today, but I often do demonstrations at the front and everybody can have a little taste. So making caramel is one of those ones I often do. I haven't brought any sugar with me to do any caramel demos or any induction hob, but that's what I normally do. And then you can see here, I usually go through the structures and what's happening in our pan when we're making our sugar. So we're starting off with our sucrose as a disaccharide. We're heating it. Usually that point when it starts to all happen is around about 160. This can then divide. We've got our glucose and we've got our fructose now, two smaller monosaccharides. And then we can do more reactions beyond that as well. They can decompose further. We've obviously got lots of oxygens, hydrogens there. We can lose a lot of water through condensation reactions. And we can create these much smaller, really volatile now aromatic flavor compounds, such as maltol, which gives toasty flavors, furans, which are nutty, diacetyl, which always fascinates me because that packs such a punch of flavor, of that sort of buttery flavor, but it's such a simple molecule. It always amazes me. And then we've also got things where we can start having polymerization reactions occurring, making these much longer molecules now, all going to have a level of conjugation in. These have got a color associated with them. They're all browns in colors, which is why we have that lovely color of our caramel as we begin to caramelize the sugar. But it's just really nice to be able to just showcase, and I do this to very, very wide audiences, often to younger audiences as well, like GCSE and A-level. Like, it's nice to be able to show them a bit of chemistry and what's actually happening in a process which they probably have done. They definitely would have eaten caramel themselves. And so it's really nice to be able to show them what's actually going on in our pan. Then back to, that's the maltol, yep. And then back to this one here, we've got vanillin, the main flavour compound, obviously in our vanilla. We've got phenylethylamine, very, very high levels of it found in chocolate. It's a neurotransmitter released by the brain during moments of sort of like excitement, which is sort of, and it's nicknamed the love drug, sort of where sort of like chocolate's got its association with like Valentine's Day and love and everything. And but the phenylethylamine you've got in your chocolate, it'll be broken down long before it actually gets to your brain. But so it's not really the reason as to why chocolate makes you feel so good. I think it's more the other stimulants that we've got in there, the other stuff, we've got lots of sugar in there as well, and that lovely sort of like creamy feel to it as well. But it's nice thing to still think about. And that really brings the end to that. And then now I'm going to hopefully, I've got plenty of time, haven't I? I'm now going to switch over to sort of like what's happened post Bake Off, mainly sort of on the science communication side of things, where I brought together the chemistry and the baking together. And so what I've got at the university now, I've got myself a science kitchen. It was an old cafe. It's outside of the School of Chemistry. And I spoke to the Vice-Chancellor of the university and the Head of Chemistry last year and said I really wanted to have a space where I can do my sort of science communication, my combining the chemistry and the baking in an actual place. And I said, there's a cafe out there. Would I be able to have that? And they gave it me. So it's all been sort of rebranded and everything. It's a wonderful space, but I've now got my own little hub where I can create content, whether I create content which goes online or onto social media, whether it's creating content to deliver for when schools come to visit, to teach things, deliver lectures for the undergraduates, whether it's to go and put together these shows that I go and deliver at external festivals, anything like that. But it's a really great space to be able to have. It's always very popular on the open days and everything, because I usually go and do a live demonstration, link it back to the chemistry that they're going to cover as part of their undergraduate chemistry course, but then they get to eat a cake at the end as well. So that's always very popular. So that is the Science Kitchen. I thought now I'm just going to show you just a few of the things that we've just done in the last sort of 12 months or so, really, even less than that, using this space. So we do a collaboration with a new scientist, which is where they come in. We're doing a 12 video series this year where they're going to come in and we do various different types of bakes, and we just do all of the chemistry, a deep dive into the chemistry behind each one of those. So that's been a really great one to do. So again, we did the chemistry of caramel, making a sponge, whipping up cream, chemistry behind bread fermentation, the flavour compounds that we've got in all of our botanicals and our herbs, the chemistry that goes on in gingerbread as well. And then things like just making some muffins, but just talking about the anthocyanin coloured pigments that we've got in our blueberries and how they can they change colour depending on pH. And we made 2 different batches of muffins where we've done them in an acidic environment with lots of lemon juice. One where we've gone a little bit overboard with our bicarbonate of soda, and we could clearly show you can open the muffins up, and inside the blueberries are stained pink in one of them and they're stained green in the other one. Really, really visual. I'll admit the green ones don't taste as good, the lemon ones are far better. But it's really nice to be able to do some of those things, and we're now sort of blending them into using some of the equipment that we've got in the chemistry lab to sort of like to really do a nice transitional step now to showcase the chemistry that's going on in a bit of a greater detail. So that's that. We've also like I mentioned, I do lots of these external sort of like shows, and really the pinnacle of last year for me was being able to go and present my own Christmas show at the Royal Institution. So this trumps Bake Off all the time over. This is such an iconic place. So many amazing people that have presented there in the past. Trust me, it was full when I presented it. That's just the photo that I took when I was arriving. But I got to go and do a Christmas baking show there. And it was all on the chemistry behind it, and it was fantastic because I did the demos, and at the end I had all the bakes available for then everybody to come and taste afterwards. We had a stampede to the exit. Everybody ate it. It was really, really great. I had so many amazing questions afterwards. And it's really, really interesting questions, especially from the younger one, which is really, really wonderful. And so, like I said, we've had amazing people of the past that have gone and spoken there. We've got George Porter, who I mentioned, and I've got on the next slide as being, he was obviously director of the RI, but he's the George Porter Chemistry Building where I work at the University at Leicester. Obviously the likes of Michael Faraday, Henry Cavendish, the amazing, iconic, Nobel Prize winning chemists that have presented in that lecture theatre, to then go and follow in their footsteps and be able to stand there and deliver a lecture was really quite amazing. I've always been an avid watcher of the Christmas lectures that are on the television. So, and there was a food link this time round because it's all about about processed foods, and you had Dr. Chris Van Tulliken that delivered those. So it was really nice to have another one that was linked to food. And like I said, the reason why I mentioned those two is because I find a really nice link that I could talk about actually whilst I was there doing that talk. And one of those is being that, so George Porter, as I said, he was director at the RI, did many a Christmas lecture. He was the Chancellor at the University of Leicester. The building that we're in is named after him. I think he did his PhD here as well. But it's part of his natural history of a sunbeam lecture, Christmas lecture in 1976. He brought a Victoria sandwich into the audience, and he was using that to sort of demonstrate the process of how we get our energy from food, the reverse of that, showcasing photosynthesis, how starch is created in chloroplast. And he had a little equation here that has cake on. So it's quite nice to be able to follow in the footsteps of somebody like George Porter, who actually had cake there. And I actually then brought cake in and demonstrated cake as well. The other nice link actually is with Michael Faraday's. He's got all of his gold colloids are in that laboratory that are underneath there. He did many series of Christmas lectures there. But the lovely link that I got to have is he'll have talked about gold colloids, whereas I talked about colloids, but in the context of whipped cream. And I talked about it in the context of emulsions and foams and whipping up cream, what's happening. But it was still colloids, and it was lovely to be able to relate it to something like Michael Faraday's gold colloids, but do something which is really relatable, because cream, everybody's tasted cream or has whipped it up at home. And I think that's where I think there's a really lovely little special sort of niche that I can do with this, whereby it really connects to that younger audience, the much younger ones, by able to see how the chemistry can relate to something that they use every day, but also then build it up and showcase something like that as well. So yeah, I did my own Christmas show. They were the things that I made. We did a chocolate Yule log, we did a meringue, and we did some gingerbread Christmas trees. Jam-packed that all into an hour's show. So that was pretty cool, and it was an amazing experience, and I would love to do some more because it was so much fun. And actually, I'm going to finish now on a little. I think we've got plenty of time. I'm going to finish now on a little case study, actually following on from this meringue, just so you can get a feel for the sort of lectures that I like to go and do to audiences to showcase the science behind the baking. So I like to set them up like this is what our target is. We're going to make a pavlova. I'll give the ingredients list. We can talk about that, and making a meringue. Whenever we also one point I will actually just add, you can see it there. When you're making a meringue, what I'd always say, weigh your egg whites. Whatever you've got, double it. That's the sugar that you want. So that's a much easier way to memorize than trying to a ratio of eggs to sugar. So we've got the ingredients for that, the ingredients for the topping, and what I'm going to do is I'm going to go now, spend 10 minutes, maybe 5, just going through some of the science behind how we make the perfect meringue, so you can get a feel for the sort of presentations that I like to do. And like I said, I would normally do this whilst also making a meringue at the front, but I haven't got that all with me today. So yeah, we're going to look at the science behind the perfect meringue. So what I do is talk about things such as going as zoomed in, looking at what is the structure of our egg whites. So in our egg white, we've got our proteins. They're around about 20% protein, 80% water. They're in there, and they're obviously in their native state, all wrapped up in that ternary structure. What we're doing by the action of our whisking, when we're whisking up those, whether it is by hand or in a mixer, we're then unraveling those proteins, we're denaturing them, we're incorporating these air bubbles. These proteins are beginning to form around this, to generate a network beginning to form around those bubbles. We go a bit further now, and we've put a lot of air bubbles into there, and you can see now we've got this complex matrix of these proteins now forming around our air bubbles. We can go one step further, and we're now having a look at the structure of the protein. We can look down at its peptide sequence of amino acids that make it up, and you can see that I've labelled these A to D in different colours, and these were here. I'm just showcasing different types of side chains that we can get on our amino acids. We can get, and I've summarised here just into 2 classes, just of if it was a hydrophobic or if it was a hydrophilic side chain. So hydrophobic being greasy, water hating, or if it was a hydrophilic one being water loving, being quite polar. And then what we can do now, we can use those to now go back to those first diagrams that I showed, and we can show how that protein is wrapped up at the start, where we've got all of our hydrophobic ones all on the inside, all mixed together. We've got our polar ones, surface exposed, pointing out, interacting with the water. Then once we now denature them, we've unraveled them now, and then we've now added in these air bubbles, and we're now beginning to form that matrix at that water air bubble interface. And we're now the air bubbles, the hydrophobic ones are going away from the water, they're going towards the air bubbles. the hydrophilic ones are pointing into the water, and that's helping to get this lovely stable foam that we have in our meringue. So it's really great to be able to do a little presentation like that to a wide audience, and then everyone begins to understand exactly what we're doing when we are whisking it up, and they'll understand why we never want to have any grease in our bowl when we're mixing up our egg whites, because if you have the grease, it's going to be really greasy, hydrophobic, and it's going to compromise this section just here. So to deflate all those bubbles, you're going to end up with a really flat meringue. So you want to have a really nice clean bowl. And we can add in a little bit of acid as well. The acid just helps with that, stabilize that structure as well. So that's really great to show. And actually, we've gone one step further. And actually, in November of last year, I went down to University of Nottingham to their nanoscale and microscale research centre, and we actually did a little experiment with our meringues. So we went and put them under a scanning electron microscope, an SEM. So I made 3 different types of meringue. We plated them in gold, and then we imaged them under a microscope to see what they look like. But we did it as a little experiment. So I did 3 different types of meringue. I wanted to see what they look like on that scale and how they compared. So here is what we've got. We've got 3 meringues. It's nice. Like I say, you can see it nice. It's comparative between all of them. So we did a classic one, just egg white and sugar. We did one where it has a little bit of acid in there, our cream of tartar. And then we have got one where we did a vegan alternative. So that's using aquafaba, which is the liquid from a can of chickpeas. The proteins in our aquafaba function in a very, very similar way, which is why they can double up very well in making meringue. I think the substitutes for eggs are really fascinating, because in this context we're using something which helps to get that sort of that lovely, nice, fluffy meringue context. But when we're doing other sorts of bakes, when we're putting in substitutes from egg, you're looking for different sorts of properties. So often things like chia seeds and things that can help make these really nice glues are used instead of something like aquafaba to help bind things together. It's really fascinating to see how we have developed all these different substitutes for various different things to cater for everybody. And again, we need from past experience, you need a little bit of acid in there. These ones are much more like a foam, so it needs that just to help hold that together. And they're all nicely colour coordinated. That was just, all that is just streaking the bag with a little bit of food colouring before piping them out. So they are all the same beforehand, but it also helped me know exactly which ones are which. So they are the same. So I knew that I wasn't going to mix any of those around. And then we went and imaged them. So we broke a little bit off, coated them in a layer of gold. We need to do that because we need to provide a conductive surface. If we don't do that, and it's non-conductive, then when you can end up, when you've then got your beam of electrons on, it can get a lot of charge build-up, it can distort that image. So we coat them in a layer of gold. It was so cool to watch all this in action. I just had such a fantastic morning there. And then we went and imaged them. And now we've got the results. And obviously, so I haven't gone and done this multiple replicates. I was as efficient as I could be in making sure that my whisking of the meringue was done for the same length of time on the same speed as I possibly could. So I've tried my best, but it's just there just as a little demonstrative sort of experiment. But the results speak for themselves, and it's exactly what I was hoping to see. So you've got here your classic meringue. You can see here there's quite a lot, very, very irregular in the bubble size and the structure of that, when you can see it all coming together. We then have the one where we added in a bit of acid, and I can tell whenever I do one that has got a little bit of acid. And you can add cream of tartar, you can add a bit of white vinegar, a bit of lemon juice, anything like that is really great. And it just helps. You get the meringue is so much easier to pipe out. It gets really just keep its definition, and it does hold its shape really, really well. And you can see there we've got these much more uniform structure in there. And then for the vegan meringue, aquafaba, we've completely replaced the egg white now. I've got something different in there. So I was expecting it to be different. Whenever I make that, if anybody's made vegan meringue, it is very, very foamy. It does bake really well. Actually, when it comes out of the oven, it looks almost quite soft, but then it sets really, really firm. But it still has the same look to it. It's not too bad in taste. It's quite nice if you just add a bit of flavouring in, actually. But it's pretty amazing how we can still get, although they are slightly bigger, as I would expect because it was visibly more of a foam, you can see there is a lot of similarity as well. And again, as a baker, with my baking head on, when we're looking to do a substitution in a bake, you want to make sure that the consumer has the exact same experience when we are switching something out. So if we are doing something that's gluten-free or vegan, we want to make sure that we can try and get the same result. So it's really nice to be able to showcase that. That's just one example. There's so many other ones that we could go and do, but it was really nice to be able to do a little experiment like that and put a little case study together. And it's really great then, because although I'm just making meringue and I can showcase that I could do it to quite a young audience of school and college students, But actually, we touched upon the concepts of protein structure, amino acids, the different sort of side chains that we've got, how amino acids are essential, which ones that we make ourselves, which ones that we have to get from food. We can go on to introduce a topic like electron microscope, and we can give us such a great depth of sort of science, but just actually link to something as easy as a meringue that everyone makes at home. So that really brings it all nicely to an end, and hopefully you've had a good feel of a bit of everything. I'm going to finish off with this slide, which actually, this just came out in the Observer in the Food Monthly last week. It was in the top 30 of something. That is a big Einstein head that I have in the kitchen. It came from the National Space Centre, actually. They were getting rid of it, and I said, I'll have that. And because it's quite a nice statement piece when you walk in the door, because everyone goes, Fuss. So, and actually we're doing something for Pi Day on the 14th of March, which is Einstein's birthday. So we're going to be doing something for that as well. And yeah, that's all of my contact details. If anybody wants to come and visit, has any ideas for a project to do together, please do get in touch. I'm always looking for new ideas and new projects to do. So thank you very much.